Okay, this is a brief chapter to follow up on the heat budget. We obviously also need to do the salinity budget parallel to the heat budget. Of course, the air-sea interactions for salinity are very different in one aspect, and that is that actual salinity doesn't leave the ocean, but water leaves and water comes in. So there is a freshwater flux, and salinity affects the density, so you have a buoyancy flux related to the freshwater flux as well. Measuring salinity was not as easy as measuring temperature, so temperature records are much longer, much more abundant in space and time compared to salinity, but more recently, satellite techniques, remote sensing techniques have been developed to use surface properties of radiances to relate to surface salinity. But obviously, the errors tend to be higher than measuring temperature and so on and so forth. And of course, salinity should be in grams per kilogram, but in actuality, the measurement is done in terms of the conductance of the water and relate that to the amount of salt in the water. So it's usually just referred to as practical salinity unit instead of the grams per kilogram. Okay, so here's a map of sea surface salinity SSS parallel to SST, which is sea surface temperature, from the Aquarius satellite, which was kind of a revolutionary satellite for the first time mapping of global salinities. And here with the cross section, I am not, hopefully I have, yeah, it's been flipped around here, but it doesn't matter. So here is the map with cross sections of subsurface salinity from Argo profiles, which is a network that we saw before. The profilers that go and stay below the surface to avoid biofouling and to avoid drifting too much, because if you go below about a kilometer, the ocean currents are really weak. So if you want a float to stay in place and not go too far, you want to go below. Plus, near the surface, anything you put becomes a fish aggregating device or gets biofouled. So these techniques are then used to move, change the buoyancy and make the profiler come up, take temperature and salinity data along the way and beam it to the satellite and go back. And it's done every 10 days, but it can be changed to do many more times a day or change the frequency and so on, depth, etc. But battery life depends on how you do it. So Argo data has revolutionized what we know about the vertical structure of the ocean as well. So that's always great to compare satellite data with things like Aquarius. Of course, satellite measures just the top surface, but the Argo tends to measure up to 5 meters below the surface, because as it gets closer than 5 meters to the surface, there is a lot of noise and so on and so forth. So there are other issues. Keeping all those things in mind, you can see the general patterns, subtropical gyres showing high salinities here in grams per kilogram, the stark contrast of the meridional overturning circulation and the salinities in the Atlantic compared to the Pacific and Indian Oceans is also very obvious. So always get such a nice map. Plus the fresh waters of the North Pacific compared to the North Atlantic, where North Atlantic deepwater formation is favored by the high salinities. And here, even though temperatures can get cold, you don't get deepwater formation in the current climate. And of course, you have lots of rivers coming in over the Bay of Bengal, and there is as much rain over here as river runoff, whereas the Arabian Sea is typically a evaporative basin, and there is the double ITCZ kind of structure that is typical of the Indian Ocean. So you can see the ITCZ and the SPCZ here as well. And of course, the Southern Ocean that looks different than the Northern Hemisphere as a channel. So if you look at the section of the Pacific here, you can see that the subtropical gyres putting salinity deeper with the convergence is seen here. And you can see the impact of this water coming down as well in the subpolar gyre here with the subtropical gyre squeezed in there, and the tropical structure ITCZs again showing up here, whereas the structure is remarkably different for the Atlantic, with the subtropical gyre and the surface salinities being very different, and the southern hemisphere being very different than the northern hemisphere also, especially compared to here. Okay, so if you take a cross section across the tropics, you can see North Indian Ocean here with the Indian Peninsula cutting through, and the Pacific section showing the east. Sorry, this is the equatorial section, so that should be the Maldives there, or whatever island is cutting it off. What latitude is this? Let me make sure. D is white areas in the bottom cross section are land masses. Okay, so it is this section here and this section there. So I should be careful before saying things. So that is the Indian Peninsula showing the Arabian Sea, Bay of Bengal contrasts, the subtropical gyre and the IPCZ impacts being shown up here in the North Pacific as well, and the North Atlantic cross section here showing again the stark contrast between the North Pacific and the North Atlantic. So I'll come back and talk about how salinity actually affects air-sea interactions and surface fluxes. It's not as obvious as temperature. When temperature is warm, especially when you're above the convective threshold, obviously the atmosphere begins to respond, evaporation, rising air, condensation, latent heating, loss from the ocean, gain by the atmosphere, and so on are all very critical. And even in the cold temperatures, for a long time, we didn't think the atmosphere would respond, but now it turns out that when there are sharp fronts, atmosphere can still respond with hydrostatic pressures over warmer waters and colder waters, creating vertical momentum entrainment and all kinds of cross-frontal air-sea interactions. So SSTs, as you can imagine, have direct impact on surface heat fluxes, atmospheric response, and coupled climate response depending on the threshold of temperature. But salinity doesn't impact the atmosphere that directly, but there are ways in which it does, and we will look at those. And it turns out that salinity also has a very close relation with the precipitation, and people have now argued that salinity measurements can be used to actually improve rainfall forecasts in models. Of course, in a coupled climate model, when you're making forecasts, it depends on how much the skill is going to be improved by using this kind of a empirical added value approach. So as far as I know, nobody is really using salinity to try to improve precipitation forecasts. But there are places where temperature forecasts are used to improve precipitation forecasts, because models in general are better at forecasting temperatures. Precipitation forecasts are complicated, as we have already talked about. The IPCC projections and historical simulations, as well as we will revisit that in the modeling module. But when the temperature forecast skill is good, the relation between temperature and precipitation can be used to use the temperature forecast to improve precipitation forecast. So that is much more direct and usable, because precipitation forecast, especially in regions like the western US, where droughts have become so persistent, can be very helpful. So it's a long story that is related to salinity, but this contrast of salinity and temperature has to be always kept in mind when we think about ocean's role in climate. Okay.